All right. Then we are going to demonstrate some binary exploitation. We are trying this new thing, this Google thingy. So if you have any questions, you can go here and ask a question. And if we have time, we can put it on the presentation and then go through it afterwards. But let's start by saying a few words about ourselves.
All right, so I'm Christian, and I currently work as a security engineer at Google, where I work on protecting some of our products from state-sponsored attackers. And I previously have experiences doing malware analysis and vulnerability research. So I have a very security-heavy background. And just as a kind of a disclaimer, the views presented here are my own and does not necessarily reflect the views of my employer. And yeah, so also very important for this presentation is that I'm a huge hummus enthusiast. So if anyone has any good recipes, please hit me up after the talk. I also do a lot of hacking competitions. That's how I got into this field, also known as Capture the Flags. And there I have a team called Bootplug, a Norwegian team.
Yeah, all right. My name is Marit, and I have two roles in my company, Soprastere. I work as a business developer, which is more or less like subject matter expert, and my specialty is secure development. And I also do software engineering with clients. I'm a board member of a security group for beginners called Oslo ZF, and then also team member of Bootplug, and then this society for women and non-binary people called Pound Girls in Norway. And yeah, also the pictures. This is a picture of Christian when he's really tired after a hacking competition. And here's me just giving up and doing some gaming instead. So today, our main goal is to demonstrate a vulnerability in Sudo. And yeah, when I say Sudo, I mean Sudo as in Sudo apt install, or like I like to say to Christian, Sudo get me a sandwich. But in order for us to make sure that everyone can follow this vulnerability and the exploit that we're going to go through, we want to start by introducing binary exploitation and just briefly talk about what it is. Then we're going to move on to explaining the stack and stack overflow, which we think is a very good segue into the heap and heap overflows. In the end, we will briefly mention some protections and preventions that you can take to your development projects. So, how many here knows a thing or two about binary exploitation? A couple of hands. Okay. Then my next question is, who have written an exploit before? Oh, only Christian? No, I think I saw another hand. Nice.
There's one here as well.
Oh, really? Cool. So obviously Christian has, because he did exploit the vulnerability in Sudo as well. But when I'm going to introduce binary exploitation, I want to do it by using the word pwn, like PWN. And pwn is what we call binary exploitation in CTFs, or hacking competitions. And if we look at the definition from Oxford Dictionary, it looks like this. Pwn means to utterly defeat or completely get the better of something. In binary exploitation, this something is binaries, right? And that often means that a program running on a server, when we pwn that program, we often get remote code execution on that server. And it is unavoidable to mention memory safety when we talk about binary exploitation. We do have a couple of memory safe programming languages such as Java, C#, Python, Rust. And we do have a couple of memory unsafe languages, such as C and C++. So we're going to look at a couple of code snippets to demonstrate the difference between these. So we start with a Python, very simple Python script. Oh, I forgot to start my timer. So I'll start now. And this simple Python script just outputs give username to standard out. Then whatever is written into standard in is stored into the variable called username, and then we print hello and the username. In which if I run it, I write Mauricio and it says hello Mauricio. But how does this look in, for instance, C? We immediately see that we require a few more lines of code. So what is happening here is that we allocate 24 bytes worth of space on the heap for the username. And when we read the name from standard in, we allow 24 bytes to be read into the username, and then we free the variable afterwards. And the point is that we need to handle memory. In the other one, we didn't have to do that. And then it's really important to make sure we know how to do it properly, because we can introduce vulnerabilities if we write it poorly, which is when binary exploitation comes into the picture. A couple of common vulnerability types are stack overflow, also called buffer overflow. We have the heap overflow, and then use after freeze, also a common one. We really wanted to go through all of them, but we don't have time. But we are going to go into details with the stack and the heap overflow. Oh, yeah, and Christian. Like, I do a lot of development projects, right? And sometimes when we talk about binary exploitation, we usually talk about buffer overflows. And then usually some in the team says, but buffer overflow is so old, it's probably not relevant anymore. Do you have any comments on that?
Yeah, so this is something I hear a lot as well. I mean, the first Stack Overflow was, I don't know, documented in like the 80s or something. So it's been a few years. So we would kind of think that the situation had improved. Just to kind of show you some statistics here, I think this was Microsoft in 2020. They said something like 70% of their critical vulnerabilities that they patch each year are related to memory safety issues. So like use after freeze, heap overflows, and so on. The Google Chrome team had similar statistics where they said something like, yes, 70% of the vulnerabilities that they patch in Chrome each year are also memory safety issues. So these types of issues account for a very high number of vulnerabilities that's being patched every year. And this is even though like we have a lot of shiny and cool defense mechanisms today, both built into the compiler and the software itself. Like for example, with Chrome, they have a lot of really crazy security features. But then on the other hand, you also have programs, especially maybe in the embedded world, that just disable all these defenses that we have developed over the years. So yeah, it's still highly relevant today.
But that's really interesting. Like you say that both Google and Microsoft, they have, most of their vulnerabilities are binary exploitation vulnerabilities.
Yep.
So it's highly relevant. And so for now, that was the introduction about of binary exploitation. If you have any questions, just raise your hand anytime. And we're going to move over and talk about the stack. So the stack is a memory region for temporary storage of data. And that's basically all I'm going to say about the introduction. And we're just going to skip straight into this code snippet. And then we're going to see how the stack looks for this code snippet. It's quite similar to the one we saw in the beginning, but we've added a user struct. It has 3 members, And when we run the program, we initialize the struct by nulling out the name member and then set the isHacker and the age members. When we read the name from standard in, we allow reading 50 bytes of characters. And for those of you who see the vulnerability, I hope you're eager to let us know, but don't do it just yet. But I've heard some rumors that we just moved to Switzerland, right?
Yeah, so
they have really good chocolate, right?
Yeah, they have.
And we do have 2 goodie bags here, and we have 2 questions today. And in just a bit, you'll be able to answer what the vulnerability here is. But let's take a look at stack first. Every function in the program has a stack frame. So the stack frame belongs to the functions. And when we first run the function, the very first thing that happens is that the function prolog sets up the stack frame by setting the return address, the saved base pointer, and then space for the local variables. The return address is the memory address in which the program knows where to go after the function finishes. Saved base pointer represents the beginning of the stack frame and also the way to access the local variables. In our program, the local variables are the struct, so we have the isHacker, the age, and the name. But when I learn new things, I often think to myself like, okay, I learned this thing, I understand how the stack frame works, and I'm able to exploit programs, but how does it really work in the bigger picture? So I asked Christian, which is kind of like my pwn mentor, like, how does it really work in the bigger picture? And I decided to draw this illustration in which every process has their own stack. And in the process stack, if one process accesses a memory address and another process accesses the same memory address, they would probably get some different data because the processes stacks are separated. In our case, we have the main stack frame, which in the process stack would be this. And I just, to be able to explain, added some more stack frames, which means that if the main function would call another function, we would have another stack frame. And if that function again calls another function, that would happen to be after that one on the stack again. And this is a LIFO structure, so when the function finishes, it's just popped out of the stack. And now it's time for some Swiss chocolate. Are anyone who wants to point out the vulnerability here? Yeah, you were really quick.
Yeah.
It's the fgets hacker name.
Yeah, it's the fgets hacker name. And why is that?
Because you have allowed up to 50 characters to be entered there.
Yeah.
And then you can overwrite first. Of course, you can write the name as you like. And then you can move on and modify the age and the isHacker. And then you can also modify the save base pointer and the return address.
All right, I'm going to stop you there. You understand the whole thingy here. So what I said is that we allow 50 bytes to be read from standard in, but we only have allocated 16 bytes on the stack for the name. So I have an illustration here of exactly what you said, which is that we can, and just ignore this for a little bit, we can overwrite the name and then into the age, and it doesn't really matter what we overwrite with. It can be anything, and we just use A's and B's and C's and so on to show you that it's for all of the variables. And we, the age is an int, which is 4 bytes, right? So we add 4 Bs. Is hacker is a Boolean, but which is 1 byte, but it's padded to 4, which is why we have 4 Cs. And then there's a blank one here. And that's because the struct is padded to 16 bytes, in which we need to add 8 more bytes to fill the struct, or for the padding. The state base pointer, we don't care what is there, but then exactly like you said, the return address is the special place that we want to overwrite. And the thing we want to put into the return address is a memory address for another place on the stack where we control the contents, so we can run our code. So what I did is, first of all, when I compiled it, I compiled, just for simplicity for the presentation, with the flag fnostackprotector. And the thing this does is to remove a security mechanism where you put something on the stack to make sure you cannot just overflow it. But this can also be, if there are enough vulnerabilities in the code, it can be bypassed quite easily. So what we did when we compiled this is to make Python print all of these bytes, and then the code we control. And when we run it, it's segfaults. But this is a good thing, because it's segfaults, and it says like code babe in what? Question mark, question mark. And the thing it's trying to do is to run the code that is on that invalid memory address. So it's just not a valid address. And then I know it's a successful exploit. Oh, and the chocolate. You can get it now. So are there any questions about the stack and Stack Overflow? We're going through it quite quickly. I mean, it can be really hard to... Yeah, all right. So for Heap Overflow, I just wanted to mention that the Heap Overflow is the vulnerability that is in the Sudo, is what the Sudo vulnerability is. But the Heap Overflow can be a little harder to understand than the Stack Overflow, so we decided to use the Stack Overflow as a segue into the Heap Overflow. And the heap uses dynamic memory allocation, while the stack uses static memory allocation. So when we compile a program, the sizes that are determined for the stack, they never change during runtime. But what we allocate on the heap can change during runtime. To mention a couple of APIs, we already saw malloc and free in the first illustration. And then for C++, we have new and delete as examples. And there are also tons and tons of memory allocators. Some examples are the glibc malloc, then the jmalloc, partition alloc, and Sudo. But the thing with all of these is that they have a trade-off between performance and security, right? So some of them uses some security mechanisms, others don't. And yeah, others uses other security mechanisms. To explain the heap, we do the same thing. Let's see how this program's heap looks like. The first thing that is happening here is that we allocate 32 bytes on the heap for the username. We allocate 64 bytes on the heap for a command. Then we copy the string command into the command variable. We do the same thing as usual, but then when we print hello and the username, we also print the time is and run the system function with the command, which in our case is date. There's a vulnerability here as well, and there will be a chocolate. You will not get another one, but so just be prepared. This processes heap, and it's very similar to the stack because every process has its own heap as well. For this process's heap, we have something called chunks because every allocation on the heap is called a chunk. And we have a chunk for the username, and then we have a chunk for the command. If we would allocate some more on the heap, we would just allocate more, use the next free memory for the allocation.
Just a quick comment here. This is based on the memory allocator in glibc, which is what we're using for our our presentation.
They all act a little different. Let's not go into. So the happy path or the intended use of this function or this program looks like this. When we run it and we insert foobar, the username chunk will contain foobar. And then the date was programmatically set, right? So it will always be date, right? And when we run it, it says hello foobar, and the time is, and the date. And now I want to ask, are there anyone who knows, understood what the vulnerability is? Okay, do you want to choose this time?
Oh, I think you were the fastest.
Yeah, you can overwrite the username and then write your own command.
All right, do you have any, no, I was going to ask if you had any commands in mind.
Well, you can print out etc shadow or something.
Yeah, that's a good point. He said you can print etc shadow or something. For our presentation, Christian came up with a cute idea, and we decided to, a chocolate for you as well. There you go. We decided to do like this. We overflow the username, and then in the beginning of the command chunk, we use a command of our choice, which is cow say hello ndc. And when we run this, using the glibc malloc allocator, this will be printed.
Yeah.
This cute cow.
This is a tiny comment here as well. You can see that on the Stack Overflow example, we were explicitly saying, please don't use this security feature. While on this one, there's no flag like that. So this is just straight up normal malloc that's used on, I don't know, most Linux distributions like Ubuntu and so on.
Yeah, so poorly handled memory, right?
Yeah.
And this, I'm actually not sure how we are on time. We started 20. Oh, I was a little fast. Then it's time for the real world example. And this is really the time to ask about the heap. If there's anything missing, because the heap is the vulnerability in the Sudo vulnerability, but there are a lot of other things that also needs to be in place. So there is a lot of things to think about. So if you have any questions, now is really in the time. Okay, I think we just move on then.
Yeah, let's
switch places.
Switch. Just gonna bring my coffee. All right. So let's head into this real-world example. This is based, like we said, on recent vulnerability from this year in Sudo. Just a note, this bug wasn't found by me or anything. This was found by Qualys. And if you like this type of research, you should really check them out. They publish a lot of really cool vulnerability research and so on. And they've found like numerous vulnerabilities in very like high profile targets. So this is a heap overflow in Sudo or Sudo edit. And Sudo edit isn't like some special thing you have to install on the side. Sudo edit is just a symlink to Sudo that's supposed to be used for only editing files and not running commands. This vulnerability allows an unprivileged user who isn't in the sudoers file or anything like that to abuse Sudo to get root privileges on the system. I can't remember like how long this bug was present in Sudo, but it was for a really long while. And just as a fun fact here, you can see on the side, me and another CTF player, we were, right after Qualys published their research, I think it was January 26th, we, started hacking on this and trying to recreate their exploit, because they only detailed the vulnerability and not like, this is how you attack it, or, create a full exploit. And in a couple of days, we were able to create like a stable exploit for this one version of Sudo. There's like slight differences between the versions. It just goes to show that like if details like this are published, you should patch quickly, because like real attackers would be able to turn this into an exploit very quickly and could abuse that to attack unpatched Linux systems. Yeah, so let's dive straight into the code. There are some prerequisites of getting to this vulnerable piece of code, but I'm not going to go into it now. If you want to look it up, you can look at Qualys' report later on. Yeah, let's start at the top in the for loop here. The two interesting parts here are to and from, and this is where we are copying data to and where we're copying it from, which makes sense, I guess. And to here comes from a variable called user args, and this is allocated on the heap by Sudo before we get to this piece of code. And user args here is supposed to be able to hold every single character that's passed as a command line argument to Sudo. So this has been, like, the length has been calculated beforehand, so this should, should be safe. And then we have this from variable, which comes from AV, and AV here comes from uargv, which is just the argument vector, or the command line arguments passed to Sudo. So let's look at the vulnerable part here. It's inside the while loop. So the while loop will run as long as we're pointing to valid characters and not a null terminator. So if we just skip the if test and look at the assignment here, we have basically, assignment and post increment, or whatever it's called. So it's just copying one character from, placing it into to, and incrementing the pointers. So if we remove the if test in the middle here, this would just be a string copy, right? We're just copying characters as long as we don't hit the null byte. But then comes the interesting part here, this sketchy looking if test. So what it's doing is it's checking, is the current character a backslash? And if it is, it checks if the next character is not a space character. And if it's not a space character, like a tab or new line or whatever, it will go into the if block and increment past the backslash. So it will basically just skip the backslash. So what happens though if the last character of this string is a backslash? Then we'll get into the first part of the check, and it will check, oh, this is a backslash, perfect. And then it will check the next one. Is the next character not a space character? And a null byte doesn't count as a, wait, how is it? Yeah, so the null byte will actually, it's not a space character. So it will increment past the backslash, and we are now pointing to the null byte at the end of the string. And the problem is though, that right after this, we're actually copying the null byte, and then we keep incrementing past the ends of the buffer. And this will also result in the user args buffer doesn't account for any more characters that's, that might be placed behind this buffer. So yeah, this is the vulnerability. Any questions? Or else I'm gonna...
Maybe this is the part where we would give some chocolate.
Yeah, maybe. Yeah, so let's just kind of look at how it, what would happen. So in this case, let's say we have the string hey backslash and then bye. And these are stored, for some reason, they're stored adjacent to each other in memory. So in this case, the code, would basically do a string copy here. It will copy hey, and then when it gets to the backslash, it will check, is the next character not a space character? And it's not, so it skips the backslash, copies the null terminator, and then keeps copying the next string in memory. So it will then copy by, and when it gets to the end of this string, it will stop copying. So we could imagine, like, for example, the destination buffer here might have, I don't know, 4 or 5 characters or space for 4 or 5 characters. But in this case, we're copying 8 instead. So here we have ourselves a buffer overflow. Yeah, just to kind of summarize the bug here. So we're copying this data from AV, and we're overflowing this user args buffer. And the user args is stored on the heap, and this is why this is a heap overflow, because we're writing more data into this buffer than it can hold, or there's a potential of writing more data. And this AV variable is stored on the stack. So we're actually copying data from the stack into the heap. Yeah. So like I said previously, like this AV variable where we're copying data from, this is stored on the stack, and it corresponds to this argument vector. Yeah, if you've written C programs, you might have seen, you know, for the signature of main, you have int argc and char argv, and these are all stored on the stack and corresponds to the arguments. So if we keep reading data from this stack buffer, from an exploitation point of view, we want to know what's stored after it. Like, can we control this data somehow? Or will the program just crash, you know, when we're copying random junk? But it turns out, so great for us as exploit developers, the environment variables are stored right after the arguments on the stack. And this is done by the Linux kernel. So when you do, you know, execv syscall, the kernel will just grab all the arguments and the environment variables and just show them into the stack, just right after each other in memory.
But dude, now you're talking about the stack, right? But we just told everyone that this is a heap overflow. So why are we talking about the stack?
Yeah, so yeah, this is a heap overflow, but it's also a stack overread. So we're actually reading more data than we should from the stack. Like, we're reading outside of the bounds of our buffer.
But stack overread? We just explained stack overflows, right?
Yeah, so a stack overflow is when we write too much data to the stack, while stack overread is just we're reading outside of the buffer. And both of these vulnerabilities can be serious, and yeah, they can lead to some weird issues. Yeah. Yeah, and another, so just an example here, you can see at the diagram at the bottom here. If we assume we have a program called test with 2 environment variables, this is how it could look like in memory. argv0 is the name of the program, which is stored on the stack, and then right after the first environment pointer would be, or the string, and then the next one, and so on and so on. Yeah, so another question we want to ask ourselves when we're developing exploits is, are there any limitations on what we can do? And it turns out that basically there's none. Like, we can put anything we want into the environment variable or environment variables. I guess there is some size limit set by the Linux kernel, but yeah, we can basically put whatever we want there. Yeah, so just to kind of, yep, okay. So yeah, we control the size because we can control like how many environment variables there are and how large they are. And we also control their contents. And one thing that you'll see later on is that we can write null bytes by just having a single backslash in the environment variables, because that's basically the bug, right? When it gets to a backslash, it will just skip it and then copy the null byte after. And this is important for the exploit later on, but we'll show that. But yeah, the question is, what do we target? Like, if you do this, like if you send just a random bunch of junk to Sudo and you trigger the heap overflow, either nothing happens or Sudo will crash, right? But we want to take this, you know, useless crash and turn it into something, I don't know, beautiful. If you, yeah, and the way that Qualys did it which was really nice. And when me and my friend were writing an exploit, we did the same thing to try and recreate their technique. And what they were doing is they were basically fuzzing Sudo, so, you know, throwing semi-random stuff at it. And what they were trying to do is they would, you know, change the sizes of the environment variables and the arguments to Sudo to try and influence how the heap looks like. And if you influence the way the heap looks like, this could turn, you know, into different types of crashes, or maybe And maybe some of them are interesting. And what they ended up finding was like they were, just crashing sudo over and over again with different types of arguments. And then they would pick up those stack traces and see like, where do we crash? Are any of these interesting? And most of them are garbage, of course. But they found this one called NSS load library. And I think this is a standard C library function. I'm not actually sure where it lives, but this function was crashing. And the reason why it was crashing was that this argument to the functions, this service user struct, which was actually corrupted. So when they tried to, dereference this library pointer, it would crash because it contains garbage, and it will just crash. So what we want to do in this case, like the reason why this function is so interesting, is the last line here. It calls DL open on a shared library. And if you've been doing exploitation, you might know that when you DL open a library that contains constructors, and this is not your C++ constructor that you might be familiar with, but rather, I don't know, I'm not sure what they're called, but like C constructors, this is code that runs at load time before main, for example. And if you DL open such a library that contains some malicious code in one of these constructors, this will run at load time. So at this point, if we open a library that we control as an attacker, we have full control over sudo. So what we want is we want to get down here. Now I've kind of removed all the stuff that's not important for this function. But if we start at the top, like the first thing we want to do is we want this if test to succeed. So we want this library pointer inside of the user service user struct to be null. And in that case, it's very nice, this function, and it will initialize it for us. And then when it gets to the next one, it checks if this lib handle is null. And this is the handle to our shared library. And it will be after first initialization. And then it gets to this wonderful chain of STP copy calls to create the shared library name. And then the name of the library will be libnss underscore, and then whatever is inside of this structure, .so, and then we have a revision, which is .2. So yeah, we'll see how it looks like later on. And this is how the service user struct looks like. It's not really that important, but just to note, the things we care about is this library pointer at the bottom here. We want this to be null. And we probably maybe want the other stuff to be null as well. Depends on what the code is doing. And then at the end, we have the name, which is where we put our malicious library name. So these two are important. Yeah, so this is how an overflow could look like, kind of like the example that Marit showed earlier, except that there might be, a lot of stuff between the user args and the service user, which is our target in this case. But yeah, this is how it could look like. We will just fill the user args with a bunch of junk, A's in this example. And when we reach this service user struct, we just fill it with zeros using the trick I talked about earlier. We just send a bunch of backslashes, and sudo will just copy a bunch of null bytes. And then at the end of the structure, we want to have, in this case, we have x/x, and then we null terminate the string. So this will craft a library name that's listed here, libnss underscore x/x.so.2. So we need to place our malicious library in a folder called libnss underscore x.
So the whole exploit is to run code from that file, right?
Yeah.
So file.
Yeah. So we're just, instead of like overriding a return address or whatever, we're just tricking sudo into opening a library that we control. Yeah. So this is how the library could look like. It's very short, very sweet. We don't really have to do, have that much code. We just mark the function with an attribute constructor. This is supported by, I think, at least GCC and Clang. And this will put the function into a special section in the resulting elf binary, which when you load it, like the dynamic loader will look through this section and run every single function that's located there. And inside of the function, we just do set UID 0, set GID 0, which sets the group and user ID to 0, which is root. And then we start a shell. So hopefully, if this works right, this will pop a root shell for us. All right, so demo time. I'm going to show you how it looks like.
Just letting you know that we have a lot of time.
We have a lot of time?
Yeah.
Okay, that's
We don't
perfect.
have to-
Yeah, then I can just waste a bunch of time. Right? Dun, dun, dun. Yeah, it's a bit weird because I don't have like a mirrored screen, so I have to stand like this very awkwardly. Yeah, so this is our basically, I don't know, exploit, our vulnerability. No, sorry, our library. It's just doing whatever I just showed you. And this is, by the way, if you're looking at your Linux system and you see like file names like this, like lol.c or something like that, just wipe your server, because all like hackers use terrible naming conventions. So yeah, that's a telltale sign. Okay, so yeah, exploit.c, yeah. Okay, I'm gonna zoom in. And just as a quick note, like this version of the exploit is not written by me, it's written by this person, so all credit to them. And the reason why we didn't choose our own exploit is because I was lazy and we wanted it to work in a Docker container because we're DevOps, and we wanted it to work between presentations and so on. So when we wrote this like several months ago, we wanted it to work, when we got here and not have some weird issues. So this exploit works perfectly for Ubuntu 20.04 with this specific version of Sudo. Yep. So let's just look into, yep. So this is, I guess, the interesting part, or I don't know, this is at least the final part, right? We're executing sudo edit with our attacker-controlled argv and nfp, which is the arguments. I can scroll maybe. Yeah. So let's see how they look like. This is the environment pointers. So what it's doing here is that you can see all of these backslashes, right? These are the zeros that we're writing. So we're now tricking sudo into writing a bunch of zeros on the heap. And then at the bottom here, we have the library name, the malicious library name. And then we have these weird thingies here. And we also have the overflow here. Oops. Copy paste. Yep. So the overflow here is there because, like I said earlier, like there might be some distance between where we overflow and this target that we have. And this basically blob of memory here is just there to kind of bridge this gap. So when developing this exploit, the person knew that, okay, so our overflow heap chunk is here in memory and our target is over here. So we kind of have to fill this space in between with some garbage. Doesn't matter what it is. And you can also see that there's a backslash at the end of that buffer, which makes sure the exploit keeps copying, or makes sure that sudo keeps copying characters out of bounds. And then we have these weird LC messages. So these are here because we want to influence how the heap looks like. So this is something we call heap feng shui, where we kind of try to craft the heap so it looks a very certain way. And these LC environment variables, they are picked up by very early on in glibc. They're picked up and they're actually placed on the heap. So by just sending a bunch of these weird environment variables, we actually control the heap. Yeah, and then we have the arguments is sudo edit -s. And the reason why this -s flag is here is because that's a prerequisite of getting to the vulnerable code. So you can read the report if you want to know like exactly how they were able to figure that out. And then we have this buffer here. it contains a bunch of garbage and then a backslash at the end. So this will kind of, when sudo is allocating the vulnerable buffer, it will account for all of these characters, but not for all the other stuff that we have lying around just waiting on the stack. So let's look at, okay. So I have a Docker container running here. Okay. So this is my user ID and GID. It's just an unprivileged user. And this is the sudo version. It's quite old now, like this has been patched, but yeah. And then we have this exploit binary, I hope. Oh, okay, sorry. Oh, that's a long path. Okay, yeah. So we have this exploit binary. This is just a compiled version that we saw before. For some reason, it's owned by root, but it's not a set UID binary, so this cannot give us root privileges by running it. Like usually it wouldn't. So then when we run it, nothing special happens, but we're suddenly root. So it doesn't look that interesting, but like behind the scenes, there's all of this black magic fuckery going on, and suddenly you have a root shell.
Are you allowed to say that?
Yeah. So finally, how much time do you have? 15
we
minutes?
have 14 minutes. So I hope you have a lot of questions. No, but you just go on.
Yep. All right. So we're going to talk briefly about some like protection and prevention stuff. But unfortunately, like we saw earlier, this is not really a solved problem. So yeah, you can make it harder for attackers to kind of attack your. If you're writing a system that's valuable to attackers, it might be a good idea to invest some time in this. If you're able and if you are interested. But it is difficult, and like what most I guess people are trying to do is make it hard or make it expensive for attackers to attack their systems, and not impossible, because that's impossible.
That's impossible.
Yeah. So yeah, you might be wondering why there's this lovely picture of me here, and it's because I had this analogy that I wanted to force into the slide. And this is me after a tiny skateboarding accident. So this is outside of the ER in Oslo. Maybe some of you have been there. And the thing was, I was riding my skateboard down a hill and I fell. So I had to get like stitches and stuff like that. But the thing was, I was wearing a helmet, so I didn't hit my head and die or something. But you can see I have a bunch of like bandages everywhere. And that's because I wasn't wearing any other protective gear, just my helmet, which you can see there on the side.
And the funny thing is that he did bring his protective gear. He had it on his in his backpack on his back, but he just didn't use them, which is perfect for the analogy, right?
Yeah, because we kind of have all of these mitigations, especially we have a lot of them built into compilers these days, which is really nice. But you still, some of them you have to opt in. You have to choose to use these mitigations and defenses. And some of them, like we saw earlier, you have to, force them off because they're on by default. So there's a lot of stuff that you can just enable, and you get some extra security just by, changing a few flags or whatever. Yeah. And also one thing you can do, which is probably not the most easy, way of
favorable solution.
Is just changing, rewriting everything in a memory safe language if you have the opportunity, or if your platform or system allows it. There's also one thing that many people are doing these days. For example, I think the Android team is doing it, and Firefox as well, is rewriting parts of their code in Rust where security really matters. So if your code, parses untrusted crap from malicious sources, you might want that code to be more hardened against attacks. So one thing that was really cool was that recently basic Rust support in the Linux kernel was merged upstream. I guess it's a while ago now. But this means that you can now write kernel modules in Rust, which makes them more safe. Yeah. In addition to like using what the compiler has to offer, you could also, implement your own security. Like, for example, sandboxing, which is done by, I guess, all browsers today are using sandboxes to parse and run, for example, JavaScript. So in the event that, for example, in Chrome, if you're served a malicious page, that's basically, exploiting a vulnerability in Chrome, the attacker would end up in this restricted environment, this sandbox. And this means that now the attacker requires another vulnerability to escape out of the sandbox. And this raises the bar and makes it more expensive for attackers to attack your system. One thing you can also do, which you kind of get for free, is to change your heap allocator. Like Marit mentioned previously, there are many that exist. And some of them are designed for security or with security in mind. So if your system, can take the performance hit, it might be worth it to check out some other memory allocators. Yeah, and avoiding unsafe functions like string copy and friends might be a good idea. They're very hard to use correctly. So yeah, I would try and use safer alternatives. Like the way I found my first Stack Overflow bug in like a real project was I did git clone, grep string copy, and there was the bug. So it's like, yeah, if you have low-hanging fruits like this lying around, like the chances are high that attackers will find them quickly.
And also just to comment, what I usually tell my colleagues and developers is that you can usually just search in the documentation for security or unsafe or something like that to find the unsafe functions.
Yep. So one thing that I really like to use when I develop C and C++ stuff is using an address sanitizer or another type of sanitizer. So we have one called ASAN. I think it's supported in GCC as well. I'm not sure. I always use Clang. Did someone say anything? Oh, okay. Sorry. Thought you had a comment. Yeah, so the address sanitizer works by instrumenting your code at compile time, and there's like a library bundled with it that basically instruments all loads and stores and so on. So when you're allocating memory, for example, it will keep track of it. So if you free it twice, like a double free, it will detect it. If you do a heap overflow, it will be detected. So the address sanitizer is really nice during development, just to catch these bugs quickly. It's more cheap, right, to catch them early on in the development process than trying to fix something. Yep. Question?
So it's you use it runtime, but you use it only for testing.
Yeah, I think that's the most common.
So the question.
Oh,
just
yeah.
repeat the question. The question was if we use it runtime or only at testing, right?
Yeah, so this is, I think the way most people are using it is just when they're testing, because it incurs like quite a large overhead. I'm not sure how much it is, but it's pretty significant. But it's very simple to enable. It's just -f sanitize equals address with Clang, and then you have address sanitizer enabled.
But
So-
we did discuss this, and we wanted to have time to add it in our presentation, but we didn't. Since I'm focused on secure development, we wanted to find some nice tools to add to your like CI/CD pipelines or just in your IDEs or something like that. But for now, we don't have any answer for that.
Yep. Also, one thing that I really like using is fuzzing. So if you're not familiar, it's basically throwing stuff at your program and trying to catch different corner cases. So especially if you have code that's parsing data, for example, if you for some reason decided to implement your own HTTP parser in the kernel or something, you should probably fuzz it to see that it can handle all of these weird edge cases and so on. And fuzzing can help you do this, especially if you combine it with an address sanitizer. the fusser will throw random stuff at your program, and then it will crash if it, just reads a tiny byte outside of the buffer. It will instantly crash and tell you this is where it crashed. So libfusser is a project by LLVM that you can use. It's relatively simple to get started with, and it's built into the compiler, so it's easy to build a fusser with it. Also, if you're doing Linux kernel development and for some reason adding your own syscalls or subsystems, you can use syscaller, which is a project by Google that makes it possible to fuss system calls, basically. And I think it's found like hundreds of bugs or something, and it's continuously running against the Linux kernel. Yep. Thanks for watching. Any questions? Yeah. Question?
Maybe it's worth mentioning, why do you want to trick Sudo into doing setuid instead of just having your own program doing setuid?
So the question was why we wanted to trick Sudo into using setuid.
Yeah, instead of just having my program will see setuid. So like the fundamental why do you in the first place want to trick Sudo?
Oh, okay, yeah, like that. Yeah. So one thing that's really cool about Sudo, like the question was with setuid, like why we want to trick Sudo especially, is that the whole concept of Sudo, right, is do something as root, basically. So if we are able to compromise this process, we instantly have root privileges. While if we target some other, a binary on the system that might be owned by root but doesn't have setuid, which means that it can kind of elevate privileges to root, even though you're running the binary as an unprivileged user. I forgot where I was going with this. Yeah, but I hope that answers your question. Yeah, basically, yeah. So if you compromise a program that's kind of owned by root, but it doesn't have setuid, there's no way for the program to give you higher privileges. So even though it's like lying around somewhere privileged, it doesn't mean that it has privileges. Yep.
I was just going to try to help answering the question.
Yeah, okay.
It's one of those few programs that have this particular except usually.
Yeah.
And it must run as roots.
Yeah. Any other questions?
No.
All right.
I guess we're done.
Yep.
Thank you.
Thanks.
Thank you.